And this is now what conversions. How would you bring about the following conversions? Ethanol to but1-ine. So first let us write down the molecules and then we'll think about the methods. We have CH3, CH2, OH, this is ethanol, and we have intentions to change it to butane, which is CH3, CH2, C triple bond CH, but1-ine. Try to look and imagine the steps you could actually conduct. Now, whenever you're faced with such questions, the first thing you must compare is the length of carbon chain. This has 2 carbons and that has 4 carbons. So first try to locate which carbon-carbon bond is the new bond. This looks like the new bond. This is the one which has been established. And what we're trying to tell you is a very popular method called retrograde synthesis. What is retrograde? Just work backwards, try to see what was there earlier. Now, I would get this if I have what? Which 2 species can react to give me this? How can I get this as a new bond? Well, obviously OH is not a very easy bond to break. Oxygen-carbon bond, if you have to remove and insert something else. What could I imagine? One imagination is this. What if I have CH3? Now, this is where you have to imagine. It is not written here and it could have more than one answers also. But say, had you had Br here or Cl, something of that kind, a halogen here, a leaving group. Okay. And what about this? C triple bond CH. And if I have minus charge here, wow, we have a nucleophile, yes. In case you mix these 2, what happens? Attack, kadak, classic SN2, and I will get this as the product. Yes, I will get this as a product. Fine. So that means that I get my 1-butane if I get these 2. Now I don't have them. All I have is ethanol. I have to prepare these. Can I prepare 1 and 2? Now let me think more. This is very simple possibility. If ethanol is divided in 2 parts, with 1 part, we just use PBr3. Ethanol with PBr3, it is halogenated to CH3, CH2Br, and the rest is H3PO3, which we don't need. So by PBr3 or PCl3 or PCl5, I will get simple alkyl halide. I can use it. So I have 1 already. Now I need 2. How do I get 2? This is not very difficult to see. That C triple bond CH minus, this looks a little ugly. Could I just get 2 from, if I have H C triple bond CH, I can remove 1 H plus, say using NaNH2, and I'll get C triple bond CH minus. Of course, there will be a cation which is pretty much useless, but yes, I would get this. But how do I get this alkyne? Now, this also becomes a problem. Let me try elimination reactions, more drastic one. How exactly? Well, if I have CH3, CH2Br, great. Else, I could also use concentrated H2SO4, 180 degrees Celsius heat, and I'll get CH2, double bond CH2, I get alkene. I have to prepare alkyne, so at least let me get to alkene. And then, if I add chlorine, I get CH2, CH2, Cl, Cl, yes. And then if I use alcoholic KOH, I get vinyl chloride. And last and the least, if I use NaNH2, because alcoholic KOH is not sufficient for elimination for vinyl chloride. So now vinyl chloride, further 1 H and 1 Cl can eliminate and I will get alkyne. And same NaNH2, if I add a little more quantity, it can also remove 1 hydrogen for me and I will get this. Is that fine? That's absolutely fine. This is the sequence and this is how I will get it. The second conversion is nothing but a subset of the first one. Ethane to bromoethene. Wow. Now I have CH3, and I have to convert it to CH2 double bond CH Br. Bromoethene. Ethene, please note. How do we do this? Well, first of all, this bromoethene. Now, there could be many ways, but I suspect we would need to use alkynes. And if we have to use alkynes, let us start at least. Alkenes are not very reactive, right? They're called paraffins. So what do? First, Cl2H nu. Let me cause a monohalogenation. I get CH3, CH2, Cl. And then I use alcoholic KOH with heat. So I get CH2 double bond CH2. Beautiful. Why do we use chlorine and not bromine? Bromine is cheap, that's why. And then I add Cl2 in inert solvent like CCl4. I get CH2, CH2, Cl, Cl. Beautiful. No, let me be a bit more rich. Let me add bromine, not chlorine. Why? I need bromo, not chloro, right? So let's not be miserly. So I get Br. I seem to be pretty close, yes. What do I need to do? All I need to do is add alcoholic KOH. If I add alcoholic KOH, one Br and one H. If I eliminate the remaining CH2, CHBr or vinyl bromide would be the answer. I don't even need an alkyne. I could just manage the alkene. This is the answer. Propene to nitropropane. Now, this is propene. And this is 1-nitropropane. How do you do this? Well, honestly, nitro group is not a very comfortable group to insert. How shall we insert that? Well, this can best be done by nucleophilic substitution. If you use NO2 minus, normally oxygen attacks. You use AgNO2 if you want nitroalkanes. Okay, so what do? I take Br and add silver nitrite, AgNO2. So AgBr will precipitate and NO2 group through nitrogen, because please remember NO2 minus is ambident nucleophile. If you want to connect through oxygen, use KNO2. If you want to connect through nitrogen, use AgNO2. Fine, I'll do that. How do I get this Br from here? This looks like one step. Now, I need to add HBr. But this looks like anti-Markovnikov addition. Yes. So use HBr and peroxide. Crash effect. So you get one bromo and that would give you one nitro. Just two steps. Now we have toluene to benzyl alcohol. This also does not look like much. We have toluene, and what we need to do is we have to oxidize this to benzyl alcohol. What is benzyl alcohol? Okay, so this H has to be changed to OH. Yes, my dear. How do we do that? Well, benzylic position is awfully easy to substitute. What do? You use bromine with NBS. NBS is N-bromosuccinimide. And when you carry out this reaction, selectively bromine gets substituted at allylic or benzylic positions. So what do I get? I get this CH2Br. Fantastic. Br has to be substituted by OH. What do? Add simply aqueous KOH or NaOH. You find that there will be simple substitution SN1 or SN2, both can proceed because carbocation is stable, nucleophile is strong. So both will be the combined mechanisms. You will get Br minus substituted by OH minus. 2 steps. That's it. And then it says propene to propyne. Now these are easy ones. This is propene and somebody says, I want propyne here. Well, you're welcome. How shall we proceed? Let's take a look. I believe we have to remove hydrogens. Then we should first fuel its aspirations. Add chlorine. Fine. Let's add it. And then use alcoholic KOH. So what do you get? You get dehydrohalogenation. H and Cl can be removed and you get this. All you need is to remove one more HCl. How do we do that? Add sodamide. Vinylic halides can be removed using sodamide, NaNH2. Very powerful base. The end. That's it. Ethanol to ethyl fluoride. Now how would you do that? Well, when you have CH3, CH2OH. Alcohols. Now CO bond is difficult to break. The first thing you're supposed to do is treat it with something like PCl3. You get CH3, CH2, Cl. But we wanted fluoride. Yes, you'll get that. Now treat this with silver fluoride, AgF. Please note, if you're treating this with PF3, you get nothing. PF3 is pretty inert, it won't react. But now you treat this. AgF is water soluble, while AgCl is not. So AgF will release fluoride ions, and now you can have a substitution CH3, CH2F, and AgCl will simply precipitate out. That would be a beautiful method for substitution. Bromoethane goes to propanone. Now bromoethane, this is bromomethane, CH3Br. And we are supposed to make propanone, which is CH3, COCH3. Now this sounds quite interesting. How should we do it? Where does this carbon go? What are the places it is going to connect to? Let's take a look and let's watch. There could be many methods, many ideas, or many, you could say, approaches for solving this. The simplest thing to add carbons, the first idea you get is use Grignard's reagent. Can we use Grignard's reagent? Well, we always can. How? Let's take a look. CH3Br can be with magnesium and dry ether. You could convert it to CH3 MgBr, right? And now there could be very different methods, you could treat this with maybe acetaldehyde, CH3 COH. If I might be allowed to use acetaldehyde directly, you would find that they would react and I get CH3 CH O minus and I get a new CH3. This is my old CH3 and this is the red one. Red one comes from aldehyde. I get this. Now what do I do? Well, add H plus, you get CH3 CH OH CH3. And now I add an oxidizing agent. Any oxidizing agent like KMnO4 or K2Cr2O7 is good. And that oxidizes the secondary alcohol to ketone. Is that possible? Easily possible. Now, this is a very simple trail. A bigger challenge happens when you claim that all the carbons in acetone must come from CH3Br. If you have any such constraint, then the problem would obviously become much more interesting. I positively believe that NCERT is not going to offer you such problems, but still, we have solved the problem once. And again, let me take it to one more, even more deep solution and discuss that possibility also. What would happen if we just want all the carbons to come only from CH3Br? Can we do that? Yes, we can. How? Again, let me demonstrate that for you. You have CH3Br and I also have CH3 groups here. Now, could I use them directly? Yups. Use zinc. So you get CH3 whole twice Zn, dimethyl zinc. Now this comes as a very interesting reagent. Yes, indeed it is. And now on this add COCl2. What happens in nucleophilic substitution? Now this dimethyl zinc is similar to the Grignard reagent, but it is less reactive. So what happens is, it is reactive enough so that it can substitute Cl atoms. So CH3 minus would come, attack, remove Cl minus, and one methyl gets attached. Then you get, the first step is you get CH3, COCl. One Cl gets replaced by one CH3 group. It is still reactive enough. So you get another CH3 substituting this, and you get this. Same reagent. I mean, this is just the intermediate step. I'm just putting this in brackets. So just add zinc, add COCl2 phosgene, and you find you directly get acetone. This is a slightly different off-track reaction, but what is the importance of zinc? See, had I used Grignard reagents, then the problem would have been that it won't stop at acetone. Grignard would further attack, give you a third attack, one more methyl will add, and you would get tertiary butyl alcohol. In case you're using dimethyl zinc, which is less reactive, it stops at ketone and it does not give you any further addition, and acetone becomes the major product. This is a second, a little difficult, but maybe not difficult, but you might not be familiar with this concept of dimethyl zinc. In case you used it, this is also a very good conversion, very efficient, very nice. But 1E into but 2E. Now this is most interesting. I have but 1E. What do? Well, add HBr. HCl is cheaper, add HCl. What do you get? You get H and Cl. This as the major product, Markovnik oxidation. And now use alcoholic KVH and heat. You would have elimination reactions, and this is beta 1 and this is beta 2. This is the major product you obtain. Is it fine? Yes, it is. T. 1-chlorobutane to n-octane. Just imagine butane to octane. From 4 to 8, you are doubling it, that means you are coupling it. You have Cl and I hope you can imagine what is exactly happening. What? You're making a bond, you're forging this new bond, you're removing Cl and making a carbon-carbon bond. This is classic Wood's reaction. You add sodium in dry ether. One step clean and you get an octane from 1-chlorobutane. As simple as that. Benzene to biphenyl, very similar. You have benzene, yes. And if you want biphenyl, what is biphenyl? This is biphenyl. How can I get biphenyl? I use Word's fatigue reaction. If I have chlorobenzene and if I use sodium in dry ether, NaCl would be removed and this gets coupled. So all I need to do is to convert benzene to chlorobenzene. And how would I do that? That's again simple. Chlorine AlCl3. Electrophilic aromatic substitution on benzene will give you chlorobenzene. And from there you can get by what splitting reaction? Biphenyl. Simple.